Hi everyone, welcome to today's broadcast. This webinar is being brought to you by the Energy Storage Technology Advancement Project, also known as ESTAP. ESTAP is managed by the Clean Energy States Alliance. The topic of today's webinar is microgrid technologies. And to begin with, I'd like to go over a quick housekeeping slide. Oh, excuse me. There we go. Today all of our participants are in listen-only mode, so we will not be able to hear you, but hopefully you can hear us. You can connect to the audio portion of the webinar using your computer speakers or a headset, or you can listen in via telephone. We recommend that you listen in via your computer to avoid telephone charges, but if you are listening by phone, we just ask that you please enter the audio pin into your telephone keypad that you should see on your screen. This just allows us to keep track of you throughout the broadcast. And today we have a lot of participants. People seem to be very excited about this webinar, and I'm sure a lot of you have questions. You can submit your questions at any time during today's broadcast in the question box on your webinar console. You can do this at any time during the broadcast. Submit your questions as you think of them. Don't wait till the end. And we will be reading through the questions as they come in, and we'll have some time for Q&A at the end of the presentations. This webinar is being recorded, and it will be made available on our website on the web address you see on your screen, cleanenergystates.org/webinars. And with that, I would like to present Todd Olinsky-Paul. Todd is the Project Director for ESTAP, and he is going to talk more about today's webinar and introduce our guest speakers. Todd, over to you.
Okay, thank you very much. So welcome everybody to this webinar of the Energy Storage Technology Advancement Partnership. This is a special webinar that we're doing specifically to introduce some folks who can give information about Connecticut, the Connecticut Microgrids program, round 2, and some of the technologies that you might be considering if you were looking to apply to that program. So I'm going to do a brief introduction of CESA and ESTAP, and then we're going to go to our presenters. Next slide, please. And I want to just begin by thanking Dr. Imre Zsuk of the U.S. Department of Energy, Office of Electricity Delivery and Energy Reliability, and Dan Borneo of Sandia National Laboratories for supporting the ESTAP program. Next slide, please. So ESTAP is a project of CESA. CESA is a nonprofit organization based in Vermont. It stands for Clean Energy States Alliance. We work with primarily state clean energy funds and help them in administering their programs. And we also work with utilities and other entities, including, in this case, US DOE and the National Laboratories. Next slide, please. This just gives you a brief overview of how ESTAP is funded via our contract with Sandia with funding from DOE. And the purpose of the ESTAP program is to create federal-state energy storage partnerships and advance energy storage in general. In today's webinar, we will be speaking about energy storage. We're also going to be speaking about some other technologies that would be appropriate for the Connecticut Microgrids program. Next slide, please. So our key activities in ESTAP, we disseminate information to stakeholders. That's what we're doing right now. And we facilitate these public-private partnerships for energy storage, helping to bring states to the table with DOE to create these energy storage projects and programs. Next slide, please. We do save these, archive these webinars on our website. This just shows you a few of the ones we've had in the past. We actually have many pages of webinars from past years archived, and they are both audio and visual in format. You can go at any time, scroll through that list, and review this or any other webinar that you'd like to see again. Next slide, please. And this gives you an idea of some of the locations where we are working with various states. We're really literally all over the map. Of course, for today's webinar, we're focusing on Connecticut and their Microgrids initiative. And if you have questions or want to know about projects in other states, I encourage you to go to our website. We'll have that link posted toward the end. Next slide, please. So without further ado, I'm going to introduce our first speaker today, Veronica Szczerkowski, the Microgrid Program Coordinator from Connecticut Department of Energy and Environmental Protection, or DEEP. And she's going to say a few words about the program, and then we will go into the main presentations. So with that, I will hand it over to Veronica.
Okay, thank you, Todd. This is Veronica Szczerkowski at Connecticut DEEP. As Todd said, Program Coordinator for our state microgrid program here. I thank you all for attending this webinar today. As many of you probably know, one of the major changes that we made between round 1 and round 2 is requiring cleaner generation where at all possible, limiting the diesel generation. So the gentleman today will speak about the different technologies that are available for the second round of this program that could help you meet the cleaner generation component of the proposals. So this webinar today is the final webinar in our educational webinar series. The other 3 webinars were overview of project financing mostly for the generation, as our program doesn't cover that. A walkthrough of technical aspects and interconnection issues with microgrids, a review of the legal and process issues for microgrids, and then today's for the generation and clean generation, renewable generation, and storage. So I thank REEBA and Paul Michaud from REEBA and Tom Bourgeois from PACE, and of course Todd Olinsky-Paul and then Dan Borneo for the storage component of today's webinar. All of the presentations from all 4 of the webinars will be posted on DEEP's website at the conclusion of the series. So after today, they will all get posted. And we should have links to the audio recordings as well on our website. So after today's webinar, if you still have questions, what should you do? First of all, if they are topic specific related to the generation for today's webinar being discussed, put them in your chat box, ask them, and we will hopefully have plenty of time at the end to get through all of your questions. Any questions you have that are program related and not generation specific, please put them in writing to DEEP at deep.energybureau@ct.gov. We need to receive all of your questions by April 18th. We will endeavor to do rolling responses and FAQs, but in all cases we'll have all the replies posted by May 1st for the program questions that we receive. So any other information you need on the program in general, please send in once again your questions to deep.energybureau@ct.gov. The link to all program information is a little bit short here, shown on the screen using a Google URL shortener, but if you copy and paste that into your browser, you will get to the DEEP Microgrid website where all program information is held. So with that, I'll turn it back over to Todd so we can really get into the meat of today's webinar. Thank you.
Okay, thank you very much, Veronica. I'm going to introduce the speakers, and I will introduce each of them immediately prior to their presentations. After all 3 presentations are concluded, we will have a question and discussion session. So I'm going to urge everyone to please, as questions arise in your mind, write them in on the, you'll see on the sidebar on your screen, there's a place where it says type messages. Write them in. Don't wait until the end. This gives me a chance to look them over, put them in some kind of reasonable order, hopefully, and it gives you a better shot at having your question be answered. We have 117 attendees at this point on this webinar, so there will be a lot of questions. We'll do our best to get to all of them. Again, when you write them in, please indicate to me if you are a potential applicant under the Connecticut Microgrid program. If you are, we want to make sure that we prioritize your questions. Not that we don't want to get to all of them, but this purpose of this webinar is really to provide this service to people who may be putting together applications and proposals under this program and need questions answered. So I'm going to go ahead now and introduce our first speaker, Paul Michaud, I hope I'm pronouncing that correctly, of Murtha, Cullina, LLP, who's going to speak about fuel cells and PV. Mr. Michaud leads the Renewable Energy Practice Group at Murtha, Cullina, LLP in Hartford, Connecticut. He has experience in all elements of renewable energy project development, operations, finance, and permitting, including drafting and negotiating complex power purchase agreements, real estate leases, renewable energy certificate agreements, equipment procurement agreements, and construction agreements. He also represents renewable energy clients on regulatory matters before state public utility commissioners and siting councils. He is the founder and executive director of the Renewable Energy and Efficiency Business Association, or REEBA, where he has extensive experience as a certified lobbyist on renewable energy policy matters. He's received his JD degree from the New England School of Law and his BS degree from Bentley University, and he practices law in Connecticut, Massachusetts, and Arizona. Paul, please take it away.
Okay, thank you, Todd. I hope everybody can hear me now. I'm up first. Anyway, I'm going to jump right into the presentation now, and I am presenting this under the banner of REEBA for the purpose of today's presentation. I'm just trying to advance the slide here. Oh, there we go. Just a quick summary of what REEBA is. REEBA is we're a very active business association, and we promote renewable energy, demand-side management, and energy efficiency in Connecticut. We now have over 70 members, and our main focus is advocacy of renewable energy and demand-side management and energy efficiency for our members, networking, and information sharing. Waiting for the slide to advance.
Why doesn't
here we
just
go.
advance your slide?
Okay, that'd be better. Okay, I'm going to focus. My purpose today is to focus. You're going to hear from two other speakers, but my purpose is to focus on the Class 1 renewable distributed generation technologies that may be able to be part or integrated into a microgrid. I'm going to talk a little bit about solar and wind distributed generation, and then I'm going to mainly focus my presentation on fuel cells. Can you move the slide, please? Okay, focusing on photovoltaic and wind first. Under the rules to be counted towards the microgrid capacity, PV and wind must be paired with energy storage, which, for example, battery storage. And however, the battery storage must be able to be utilized 24/7 when islanded. As you probably know, and hopefully I'll be corrected during the storage presentation, but there are current limitations on battery storage technology where we're not sure if it's economically feasible for batteries to be run 24/7 when islanded. The technology is going forward substantially, but we don't know if we're there yet in time for this microgrid. So we're not sure if either solar or wind will be able to be counted towards the microgrid capacity. Next next window, please. The good news, though, however, is solar and wind, and especially solar, can be a subset of a microgrid generation system. It could be used as a green enhancement for a microgrid. And what this means is under current technology, you can, for example, a solar system, you can actually integrate it into the microgrid by using a reference voltage, such as a fuel cell, where if the system gets islanded, you still can run the PV or wind under the island mode, again, as long as you have a reference voltage, including a fuel cell. But even if you do that, it can't be counted towards the microgrid capacity, but it still allows, again, solar or wind to be included in the microgrid, generation in the case if the system goes islanded or even when it's grid connected. And an important reason, especially for PV, why that might be important, because under Connecticut's current incentive structure, PV actually can save, your typical, 700, 600 kilowatt system on a rooftop of a school, for example, can actually save about $1 million over the course of a 20-year PPA contract. So it actually can not only help give a green enhancement to the system, but it can also help generate savings for the whole system, the system as a whole. The next slide, please. Okay, so now I'm going to talk about fuel cells. Fuel cells are, in our opinion, are a great generation option for microgrids. They're ultra clean. They are a Class 1 renewable energy resource in Connecticut. And as Veronica indicated, 75% of the generation must be from a Class 1 or Class 3 source. And what's really nice about fuel cells is they're a Class 1 renewable resource. They're very high efficiency. For electric only, they have a 42 to 50% LHV, which stands for lower heating value. And what this means is it's the energy per therm of natural gas. And they get even more efficient when you do CHP fuel cells. The system efficiencies run from 55 all the way up to 90%. So the combined electric and thermal, with the combined electric and thermal, you get more energy per therm of natural gas. And for example, my understanding, the Claridge Power fuel cell is upwards of 90% efficiency, which is very, very high. Fuel cells have a relatively low operating cost. They have very few operating moving parts. It's a chemical reaction. The capital cost for a fuel cell is slightly higher than your traditional CHP, for example, unit, but the life cycle cost is very competitive, again, because of the very low operating costs. Next slide, please. Fuel cells have a capacity factor of 80 to 95%, and which is very high compared to other renewable technologies, and they run over 90% of the time. They also have a continuous grid operation, with or without the grid. This means they run base load when you're just in the grid operation, and then they continue to run when you go into the island mode. And this creates a very viable economic model for microgrids in Connecticut. Not all fuel cells, but select fuel cell technologies can be load following, which is required, I believe, under the rules. Next slide. Again, with many of the select fuel cell technologies in the state, you can do preventive maintenance on these systems, and it can be done while the fuel cell continues to run base load, which is a great advantage. I already talked about the competitive life cycle costs versus traditional CHP. Again, fuel cells are cleaner than non-renewable CHP. And a really important thing to note here too, from a legal perspective, siting perspective, fuel cells are exempt from air permitting requirements. And this could really speed up the deployment process, since under Connecticut law they are exempted from those requirements, and it really will save time on the back end or on the front end. Next slide, please. The table here is here for you to see that fuel cell generation facilities do substantially reduce emissions, greenhouse gases, and energy use for a microgrid system. Next slide, please. This slide shows a few, certainly not all of them, and there are a lot of newer fuel cells, including, I believe, the Yukon microgrid fuel cell that's online now. But this shows, the purpose of this slide is to show that in Connecticut, especially in Connecticut, fuel cells are very common. They have been used for several years, very successfully in Connecticut, and they've really shown that they operate very reliably. Next slide, please. Fuel cell, an important note is fuel cells do meet DEEP's generation requirement for microgrid funding. They are a baseload technology, and they can be used as part of the included in the microgrid generation capacity. The important aspect of fuel cells is their financial flexibility. And what that means is, for example, with many of the fuel cells that we've worked on, they can use a power purchase agreement. And for those of you who don't know what a power purchase agreement, it's where, and it's really important when you're dealing with municipalities, because a lot of municipalities, they don't want to bond, they don't want to bond these large, relatively expensive capital costs for generation systems. They don't want to bond it. They don't have the money to pay for it. So with a PPA, a third-party developer actually owns the fuel cell located at the site at the municipality, for example, and under the agreement, they sell the energy back to the municipality or the critical facilities at a set, a determined electric rate, or an electric rate with a tolling arrangement for the gas. And this way the municipality can simply buy the energy, or the energy and the gas, and they don't have to put out the capital cost of the project. And again, most municipalities in Connecticut find that a very useful way of having these systems installed. Other financial options available are, again, the lease-to-buy option, and then the lease-only arrangement. Fuel cells, because they're a Class 1 generation technology, they qualify for Connecticut's low emissions renewable energy credit auction program. And what that is, they do, because they're Class 1, they generate renewable energy credits. And each credit, a credit is equal to 1 megawatt hour of generation. And under the auction program, a fuel cell can qualify for, if it wins in the auction, which the next auction is actually coming up in April, and it should run through the summer, but there's one every spring. If you do win, are selected in the auction, you get a 15-year contract with either CLMP or United Illuminating, depending on what service territory you're in. And what you basically, under that contract, you basically get you sell your RECs to the utility under the renewable portfolio standard, and the going rate for fuel cells, I believe, is around $55 to $65 a REC. So that can create a substantial cash flow for the project. And in Connecticut, CESA is the state agency that funds renewable. They're coming out with some options now to help fund fuel cells that use microgrid with microgrids. Next slide, please. I think a really important thing, thing for everyone to know who are not in Connecticut is that state policy strongly favors fuel cells. So why does state policy favor fuel cells? Because in Connecticut, two of the major fuel cell manufacturers, they're located here, or they have major manufacturing facilities here. So there are a lot of incentives to do fuel cells in Connecticut. So there is a very supportive regulatory framework here that make fuel cells very economical to use. I'm going to list here. I have a list of a few of the incentives. I already talked about ZRECs, but Connecticut has a 2 megawatt net metering rule, which means that you can have a fuel cell generate, or a fuel cell can generate base load, and you can actually overproduce, and it's actually a yearly reconciliation at the end of the year, where as long you can actually sell any excess power back at the wholesale rate, which is part of that. There's a virtual net metering statute, which was just expanded, where you can actually locate, and it applies to states, municipalities, and agricultural land. For example, you can have have a fuel cell located in one place in the town, but they can actually sell the energy virtually when you're not sort of in the grid mode, or in the grid mode, to up to 5 other critical facilities in the town, and it can be done virtually and not actually be interconnected. So that's a benefit. There's a standby charge waiver for projects equal to.
Paul, Paul, I'm sorry to interrupt. I just want to let you know you have about a minute left.
Yep,
2 minutes. Okay, thank you.
Okay, I have 1 slide left. There's a standby waiver. There's a natural gas rebate waiver for fuel cells, and there's a demand charge waiver. And these all reduce the cost of for fuel cells. Next slide, last slide, please. And this is my last slide. This applies to probably all generation, but there's obstacles and opportunities to fuel cells, interconnecting into the microgrid, who owns and operates the fuel cell, especially if you're going to use a PPA, you have to determine those factors. How do microgrid customers of the fuel cell pay for the power? Again, under a PPA, you may have more than one customer, and you have to determine how you're going to allocate the cost of the power to those projects. And again, with other projects as well, there's also not air permitting, but there is siting things you have to think about too before the Connecticut Siting Council. Next slide, please. With that completes my presentation, and I'll pass it back to Todd now.
Okay, thank you very much. Before introducing the next presenter, I just want to say again that if you have a question, please send it in. Don't wait till the end. We now have 128 attendees, and we're going to do our best, but it would be helpful if everyone sent their questions in when they think of them, and please identify yourself if you are as a potential applicant to the Connecticut Microgrids program when you do that, so that we can prioritize those questions. Also, I believe Veronica wanted to clarify something about the program. Veronica?
Thank you, Todd. And Paul, I may have misheard you, but I want to be sure that everybody is clear. While the microgrid program for round 2 is limiting diesel generation to 25% of capacity, and today's topic is on clean renewable generation and storage, we do allow into the program other types of generation, such as microturbines or reciprocating engines, that kind of stuff. So I want to be sure that everybody understands that while we do value highly our clean and renewable generation, we will allow in other types of generation beyond diesel into the program. And I just wanted to make that clarifying point, so thank you, Todd.
No problem. Thanks for clarifying. So I would like to move along now to introduce Dan Borneo of Sandia National Laboratories. As I mentioned earlier, Sandia contracts with CESA for our ESTAP program, so we appreciate their support. And Dan is going to speak about distributed energy and electrical energy storage. Dan is an electrical engineer and principal member of technical staff at Sandia National Laboratories in Albuquerque, New Mexico. He holds a BSEE and MSEE from the University of New Mexico at Albuquerque. And in 2012, he became a scholar in residence at the University of California, San Diego, where he consults with the university on their energy storage program. At Sandia, he serves as the principal investigator and project leader for the Department of Energy, Office of Electricity, Electrical Energy Storage Systems Demonstration Program. His primary focus is collaborating with representatives of the energy storage industry, academia, and state energy groups to facilitate moving innovative electrical energy storage technologies and systems to commercialized products and services. So, Dan, if you're ready, take it away.
Okay, thank you, Todd. Thank you for that lovely introduction. but you just decreased my presentation time by a minute. So I have, once again, I have more slides than time, so I'm going to move along. This presentation will be available to you afterwards, and you'll find more information in the appendix at the end to help anybody make their decisions whether or not to include energy storage into their proposal. So what I'd like to talk about is look at a little bit at the applications and benefits of energy storage in a microgrid, and then some project considerations around the design, the project team, testing and commissioning, and then just give a little brief look at some of the technologies and systems that might be best suited for a microgrid. And I hope that I probably won't answer many questions, but I'm hoping I will stimulate more questions. So moving on, some applications and benefits. This picture is for all you Northeasterners that just got through a hellacious winter. So we'll talk about some of the benefits here. So number one on our list is the power quality, the UPS. So energy storage can provide ride-through in the event of momentary power glitches, and if it's designed right, even longer than momentary power interruptions. It also can reduce the demand, the peaking demand on a distribution equipment and lines. As was noted, it can provide dispatchability to your renewables. And yes, I do not expect anybody that would put in a PV system with only a battery to back it up. That would be very cost ineffective. So I would lean more towards the renewables with an energy storage along with other distributed energy resources, whether they be natural gas generators, fuel cells, CHP, whatever. And then, but that leads to the last point, the generator support. One thing that energy storage can do is, if it's designed correctly, it could be used to reduce the generator runtime and increase the efficiency of the generator. And once again, energy storage, it is expensive, so the more applications you can utilize it for, the more cost effective it's going to be for you. So just to give a little bit of brief on those points with pictures, this drawing here, this graph here is actually an automatic generator control command signal graph, but it does point out how the energy storage works. And if you look at the graph on the right-hand side, you'll see that basically that AGC command is the load. That's the green line. The red line is the energy storage device. You can hardly see the red line because it is right on with what the load is doing. So this gives us our instantaneous response, great for power quality, ride through, and it also helps to firm generation such as wind and solar. And then demand reduction, utilizing your energy storage as a load to make your generation run more effectively, or utilize more of your renewables, and then as a generation to either reduce the size of your generation or maybe replace it for periods of time. And then the PV intermittency, I'm sure you all have seen these graphs. If you look at the magnifying view at the bottom, you'll notice that the PV data is in white, the battery is in red, and then the green is the output. And you'll notice that the variability of the PV is smoothed out to an extent by the battery to have a little better output. So now we'll just talk about a little bit of the design considerations. So the microgrid, what is a microgrid? Basically, it's anything that has some form of generation attached to it that can be isolated from the main grid. And there are more drawings like this in the appendix. I'm only going to look at this one just to give a brief overview of what I picture in my mind. for a microgrid, basically you have your distribution, you have your battery, you have your distributed energy resources, whether they be generators, fuel cells, CHP, renewables, whatever. One thing to note is that in the red you have the IEEE 1547. Most inverters are required to shut off in the event of a power outage on the grid. If you want to do idling, this is a problem. I've been doing some research on this. It looks like the inverters can be reconfigured to allow ride-through, but your utility may still require the 1547 compliance. In that case, you would need to provide a relay or some sort of tripping mechanism up in your main feeder breaker that will isolate you from the grid and allow your battery to operate with your distributed energy resources. So some project considerations in the design. You need to understand what applications you want to use your energy storage for, design it appropriately. You want to optimize how big the size and power rating is and for how long you really need it to do your job. Some technologies are better suited for long durations and others for short durations. You need to worry about the control. It's going to get probably a little tricky when you're trying to control distributed energy resources and energy storage. You like to see one master controller controlling all components. And also, one thing that's not talked about a lot is utilizing your energy storage to offset any fuel generation, decreasing your fuel consumption. And then with many of the newer systems, they're still working on the UL listing. That's a problem in some installations. Your authority having jurisdiction may want UL listed. You have to deal with that, and I'll talk a little bit more about that with the project team. And then what codes and standards are required to install the energy storage, what inspections are required for the interconnection for your local inspection. And then in some of these systems that are more detailed, you will need a construction and installation design package. And then this last bullet here is an energy storage specification. We're working on trying to come up with generic specifications that people can utilize to tailor to their needs, but when you go out to buy your energy storage system, you should have a nice detailed specification indicating what it is you want. So the project team, system integrator, probably the most important part of your team. You should have one that's going to integrate the entire system. Your design team to develop your construction drawings, obviously your vendors that will provide the system, the startup, the warranty and service, your authority having jurisdiction. If you have something out of the ordinary, they're not used to seeing it, bring them in, get them involved at the get-go. It'll be a lot less painful for you than when you're done. You call in the inspector, they're looking at something they've never seen before, and it doesn't pass inspection. Same thing with the first responders and your insurance man, right? We're hearing from firemen that says, hey, we need to understand how to deal with these battery systems in the event of emergency. Your insurance underwriter needs to give you a policy. He needs to understand what it is you're doing. And then you need your local power company to look at the interconnection items. And then testing and commissioning. I cannot stress this enough. Sandia through DOE is getting very, very involved with this testing commissioning part of it to make sure that the systems are installed and they operate safely and reliably. You should do a full commissioning on the integrated system. You should have a commissioning plan talking about the factory acceptance testing, doing as much testing as you can do in the factory before it hits the field. Then once it hits the field, verifying that it was installed as designed, that everything is complete. Was it, are all your connections torqued? Did it meet all the code, the standards, regulation? Do you have all your safeties in place? And continuing on with testing, then you have your operational acceptance testing, your OAT, that's do all the individual components operate as required. Then your functional acceptance test. Does the system operate as a system with other microgrid components? Do you have the right control? Does it do does it perform the applications that it was designed to do? And then a shakedown portion, and that is basically shutting the power off, doing the anomaly type things to see that the system it shuts down in a controlled manner and restarts in a controlled manner, and that all your safeties operate, all your enunciations operate, etc. And so real quick, with the last couple of minutes I have, we'll look at some technologies. These technologies are ones that I'm familiar with. I am not endorsing any of them, but I do have experience with these ones. So just at top view, you got your lead acid, your advanced lead acid. The advanced lead acid usually has a carbon component, and we have found that carbon component has added thousands of cycles to the life of a traditional lead acid battery. Been around for 100 years, rock solid, a good choice if you want something that's going to work. New kid on the block is making a lot of inroads. It's lithium ion. Traditionally, they have been a shorter duration type battery, up to 15 minutes, and I neglected to say the lead acid can go anywhere from short term to long term depending on the design. And then back to the lithium ion, we are now doing some projects. One in California comes to mind where it's going to be an 8 megawatt, 4-hour lithium ion installation. So lithium ion is now making inroads from the power portion, which is less than 15 minutes, to the energy, which is greater than 1 hour. And then you have your flow batteries, zinc and vanadium flow. These are similar to a fuel cell, and they have thousands plus cycles, and they're starting to get more play time. And then here's a GS battery, a little example of a 60 kilowatt 1 hour system that we tested for a forward operating base in the military, but it could easily be used for a small microgrid situation. This system here is lead acid, but it also could be converted into a lithium ion, which would give you a little bit higher kW rating and maybe even a higher power energy output, energy duration, I'm sorry. And then here's a picture of a ZBB zinc bromine flow battery. This is a 125 kilowatt 2.4 hour system that we are installing at the University of California, San Diego. It's supporting a 30 kilowatt PV. And then this is a bigger system. This is an Enervault 250 kilowatt 4-hour iron chrome flow battery that's being commissioned in Turlock, California. The tanks you see there are their electrolyte. Sitting behind there is some trailers, 2 20-foot trailers, or maybe it's 1 20-foot trailer with all their battery cell and their electronics. And then here's one from Eagle Picture. The important section here is in the bottom left-hand corner, their power pyramid system, where they're actually taking and doing hybrid solutions with both lead acid and lithium ion, and it provides you multiple applications. So you have your lithium ion doing more of the short cycle, and then your lead acid doing more of the medium and long cycle applications. And so cost considerations, I'm not going to kid you, energy storage is not cheap. The capital costs would include the design, permitting, the site infrastructure preparation, the energy storage system itself, the balance of plant to make it run, and the installation of it. Operating costs, you have your efficiency factors. So if you're charging these batteries, you don't get every kilowatt hour you put in, you do not get out. So you have some losses there. You have to consider the cycle life, how often you have to replace it, the operations component, the maintenance, and then the debt service for financing. So in summary, so ES is needed for renewables to be counted towards generation. That's part of the RFP. So energy storage can help in that regard. You need to understand what applications you want to use energy storage for. Try to maximize the number of applications. You need to optimize the KW and the KWH rating. That's the power and energy rating. There's some tools out there, DNVGL, to give them a little plug, has an evaluation tool. There's Rick Fioravanti's email that you can talk to him about how they might be able to help you. Energy installation, energy storage is a new installation, so you're going to have to worry about things as your insurance man, your codes, your standards, your utility interconnection people, your inspectors, your first responders. And then please, please have a robust commissioning plan. These are some commissioning plan is something that Sandia can help. Todd and I are talking with Veronica to see, since we are supporting the RFP process, we have to be careful about how we help people. But we're looking at ways of helping people that are involved with energy storage projects and how we can help them. But we provide commissioning, consultation, and then independent third-party verification. So with that, another thank you to Dr. Zook for funding me to be here. Questions I will answer during this process, and then further questions, as Veronica said, through the RFP process. And once again, there's more information in this deck that you can use, you can look at your own leisure. And that's it, Todd. Thank you.
Okay, thank you, Dan. As Dan said, the slides, there may be more slides than are being presented, and because we are on limited time, and so when these are posted, they'll be posted to the CESA website and to Connecticut DEP's website. You'll get those full decks. And again, we are getting a bunch of questions. Please indicate if you are potentially applying to the program, and we'll prioritize answering those questions from applicants. I'd like to now introduce Tom Bourgeois from PACE Energy and Climate Center, who's going to talk about CHP systems. Tom is the Deputy Director at PACE Energy and Climate Center in White Plains, New York. He's researched and written extensively on microgrids, combined heat and power, or CHP, distributed generation, demand response, and renewable energy. He serves as co-director of the U.S. Department of Energy's Northeast CHP Technical Assistance Partnership and is co-chair of the New York City Mayor's Office of Long-Term Planning's Distributed Generation Working Group for 2012-2013. And he is among a group of experts assisting New York State in preparing the New York State Microgrid study for completion in spring of 2014. Tom has contributed to more than a dozen CHP studies and reports, as well as numerous briefs and other submissions to the Public Service Commission in New York and the Department of Public Utilities in New Jersey. In 2008, he received the U.S. CHP Association's CHP Champion Award. And I want to say that I had the pleasure of working with Tom for several years at PACE Energy and Climate Center. So we're very happy to have you presenting today, Tom, and I'm going to pass it over to you.
Thank you very much, Todd, and thank you all for participating today. I appreciate this opportunity to work with ESTAP and Dan, Paul, and Connecticut Deep as well. Do I have control here?
Yep, double click on the mouse there.
Okay. I'm double clicking, and I don't seem to be able to move the slides for some reason.
Okay, try one more time. Just double click on the screen.
Yeah, I'm double clicking and
all right, well I can advance the slides for you if you just say next.
yeah, this just does not. Okay.
Sorry about
Next slide, please. Oh. Next slide.
that. Sorry, there's a bit of a delay.
Yeah. Okay, thank you. First of all, let me introduce, I'm representing the CHP Technical Assistance Partnerships, who we are. We are one of 7 centers around the country. We cover New England states and New York State. I'm working along with the UMass Amherst Graduate School of Mechanical Engineering, and our sponsoring institutions include the state of Connecticut, CEPIA, Massachusetts Department of Energy Resources, and NYSERDA in New York State. We're a consortium of regional CHP experts. We provide fact-based, unbiased information on combined heat and power CHP, the technologies, project development, financing, local electric and natural gas interfaces, and states' best practices and policies. Next slide, please. Our centers offer support in several areas. We do market opportunity analysis. We have several areas in which we're doing specific opportunity analysis and market outreach studies. We do technical assistance. I'm hoping that might be valuable to some of you on the line today. We provide technical assistance to end users. By that, what I mean is we do have tools, modeling tools, for both what we call qualification screening, which is a first stage look at the technical viability, economic feasibility of a potential CHP project within a municipality or microgrid site. And we can also do much more detailed technical analysis at the site. So there's 2 levels of analysis. Both are available from our center through modeling tools that have been vetted and operated for many years. I forgot to say that we've been doing this, we've been running the center since 2004, so we've been doing it for more than a decade here in the Northeast. Next slide, please. So CHP can be the centerpiece of a community microgrid. In this depiction, we're looking at a potential microgrid that might include a hospital, with a combined heat and power generator on site there, tied in perhaps with energy storage and also perhaps serving a retirement home, a supermarket, and also tying in renewable distributed generation, small wind or more likely PV. So this is, we see this as a potential centerpiece of the community microgrid. Obviously, it doesn't work in all types of circumstances and all applications. Later on within this presentation, I'm going to address those markets and areas where the opportunity is best. But if you do have the circumstances that are right for the development of a CHP system, it can help significantly improve both the efficiency of your community microgrid as well as the profitability, the economics, the rate of return, and the payback on a microgrid. So for all of those reasons, we would strongly encourage you to take a look at the opportunities for combined heat and power when you're developing a proposal, should those opportunities be there. Next slide, please. So what is combined heat and power? I'm assuming that some of you on the line here today, some of the audience is not entirely well-versed in what it is. CHP is an integrated energy system that's located at or close by a building, a factory. It generates electrical and or mechanical power, and most importantly, the benefit of CHP is it recovers the waste heat that's otherwise dissipated to the atmosphere or to cooling towers or to bodies of water. That heat is recovered and utilized in a productive manner for heating, cooling, or dehumidification. And CHP can utilize a variety of technologies and a variety of fuels. Next slide, please. To try to drive home this a little bit further, this is a a depiction from the U.S. Department of Energy, fuel utilization by the U.S. utility sector. And what we see here is that more than 2/3 of the fuel used to generate power in the United States is just lost, wasted as waste heat, conversion losses of nearly 2/3. So in essence, for every 100 units of energy we put into the system, we throw away 67 units of energy, and we only productively use 33 units of that energy. So the beauty of CHP, where it's viable, is that it can take that wasted 67 units of energy and recirculate it and somehow use it in a productive manner within your building, within your microgrid. Next slide, please. Oh, okay, so why should we care? Well, CHP, as I was mentioning, recovers much of that waste heat. It greatly increases the overall efficiency of energy services. Again, this is a depiction of a, let's call it a business as usual, where we typically have a power plant where you're getting utility power, and you have on-site boilers providing your thermal energy requirements. The boilers might operate at 80% efficiency. The efficiency of the electric system may be about 32%, including T&D losses. So in this instance, what we see here is a total, and we're at the CHP system will take in about 100 units of fuel and provide the same amount of energy as 150 units of input, MMBTUs of input energy as the traditional system. So in effect, you're getting about a 50% increase. The CHP, appropriately designed, appropriately sized, and once again, we want to stress that, and we help with this, we have tools to help with this, that this doesn't work everywhere, but where it does work, you can get marvelous system efficiencies. You can increase by nearly 50% or more over the traditional method of purchasing your power directly from the utility and then purchasing separately your thermal requirements. Next slide, please. And so by doing this, because of the significant efficiencies of CHP, and CHP can both be renewably based. Paul mentioned and gave a great presentation on fuel cells. Fuel cells are a great application for CHP. CHP can also be biomass based or renewable. The more widely used instance of CHP is natural gas-based CHP, but even there, even utilizing natural gas, because of the significant efficiency gains, some 50% or more gain in efficiency, greenhouse gas emissions can be reduced by 30 to 55%, depending on the application. Next slide, please. So once again, CHP results in higher efficiencies, results in energy savings, results in it can result in reductions in criteria pollutants, and it does so with a much smaller footprint. We are strong champions here of renewable energy and PV, but what this chart is designed to show, and this is from a report, CHP, a Clean Energy Solution, that was prepared by the Department of Energy and the EPA. This contrasts 10 megawatts of CHP using natural gas combustion turbine with 10 megawatts of PV, 10 megawatts of wind, and 10 megawatts of natural gas combined cycle. I think the strongest takeaways here is, first of all, the total system efficiencies. The CHP will run at about a 75% total system efficiency, the gas 50%. The annual capacity factor for CHP is far greater than the renewables. And the most important point, line 3, the annual useful heat produced. This is the essence of CHP, capturing and reutilizing in a productive manner that waste heat for purposes like space heating, hot water heating, driving absorption chillers, process heating for industrial, sterilization for a variety, or laundries for a variety of different purposes. And CHP does so at a fairly low capital cost in comparison with some of the renewable technologies. Next slide, please. So again, what are some of the technologies that are employed in CHP? The equipment might include reciprocating engines, turbines or microturbines, gas combustion turbines or smaller microturbines, steam turbines, and as Paul presented, fuel cell applications. Fuel cells, once again, are a great application for CHP. This would be tied together with heat recovery systems, recovering hot water, recovering steam. And as I mentioned earlier, you could have thermally activated technologies, absorption chillers, desiccant dehumidification, or thermal storage, which allows longer hours of operation, full season operation through both heating and cooling seasons, and also allowing you to reduce investments in chillers as well. Next slide, please. So CHP is combined heat and power, the on-site simultaneous generation of two forms of energy, both heat and electricity. And once again, that heat can be used for cooling, so it can be actually trigeneration, heating, cooling, and power. And this is from a single fuel or energy source. This particular diagram shows conventional CHP, also referred to as topping cycle CHP, direct fired, or some might call power first CHP. So you have fuel in to an engine or a turbine, a generator generating electricity first. That heat is then recovered through some heat recovery unit. It's captured as steam or hot water, depending upon the technology. If one needs a lot of high-quality heat, for example, for the production of steam, you might be using gas combustion turbines or some types of fuel cells. Lower quality heat reciprocating engines may fill the bill quite well if you don't need a lot of steam. And then again, providing cooling, heating, and power to a building or a facility. Next slide, please. Okay, here's another case I mentioned earlier, the topping cycle. This is waste heat to power CHP. Also, one might refer to it as heat first CHP. And in this instance, we're looking at fuel coming in and heat being produced first for perhaps an energy-intensive industrial process, heat produced for that process, and then that waste heat from the industrial process being captured in a heat recovery steam boiler, a steam turbine, and then utilizing that waste heat to produce electricity. So in the first graph I showed you a moment ago, it was electricity first production. In this case, a bottoming cycle or a waste heat to power, a heat first CHP application. Next slide, please. Attractive CHP markets. CHP, we want to stress, is not the right solution in all instances. As I said, we're trying to identify those cases where it's most technically viable, economically feasible. And these are some of the applications where CHP might be most attractive. In the institutional sector, this might be of most interest to many of you on the phones. You'll see that this is quite appropriate to hospitals, to schools, to colleges and universities, water and wastewater treatment plants, and so on. Also, multifamily apartments, data centers, supermarkets, and in a wide range of industrial applications and some agricultural applications as well. Next slide. Now, CHP is not an untested or unused proposition. CHP is already widely utilized throughout the United States. CHP, there's some 4,200 CHP sites. For these figures, I'm utilizing the ICF EPA CHP database. As of 2012, we have about 4,200 sites in the database, about 82, 83 gigawatts of installed capacity. And that's already producing huge benefits nationally, including saving about 1.8 quads of fuel each year, avoiding 240 million metric tons of CO2. And just to give you a sense of where it is, about 87% of the capacity is industrial. 71% of the capacity is natural gas fired. However, it's a little bit, that figure is a little bit misleading, as much of the CHP went in first into industrial applications. So 87% may be in industry now, but there's a lot of great applications, and we're seeing more and more in the institutional, hospital, college, university, and commercial sector as well. Next slide, please. So why does CHP make sense for a microgrid? Well, CHP continuously operates 8760 hours per year. It efficiently provides both electrical and thermal energy. It provides, if appropriately designed, configured, and operated, it provides resilient power through storms, blackouts, and other emergencies, as I say here, when it's designed to do so. And microgrids can be used to, this is the key point, microgrids can be used to improve economics, municipal economics, by providing a cost-effective alternative to the existing aging grid and higher cost of electricity. If you can generate power, you reutilize that waste heat in a productive manner, capture a significant fraction of it for thermal needs, it can greatly increase the return on your investment in the project. Now, Connecticut has long been a leader in this field. We have a little box here down to the lower right, which shows we did some analysis of the CHP database. In Connecticut, the number of new installations over the last 5-year period, Connecticut was number 3 in the country with 64 new installations. And if one were to normalize that for the size, Connecticut is behind California and New York, but California and New York are far bigger states. So normalized on a size basis, Connecticut is clearly a national leader in CHP installations. Next slide, please.
Now, what Tom, we're running a little over, so if you could
okay,
try to
I'll quickly go by this one. I'll go to
okay, thank you.
Backup generation, go to the benefits. We like to say that CHP is proven, reliable, economic, and clean. It lowers energy costs. You can take a look, folks. This will be posted, and we have a lot of resources at our PACE website as well as our DOE. But I'm just giving some examples here of trying to highlight the point that it's proven, reliable, economic, and clean. Improving return on investment, lowering energy costs. We have examples here from New York Presbyterian, South Oaks Hospital, a microgrid in upstate New York with a $300,000 to $500,000 annual savings, and this is an existing microgrid that one can look at. Next slide, please. CHP in a microgrid might be particularly attractive. What we're trying to display here is that if you have a couple of buildings in close proximity, and those buildings have what we call complementary loads, that you can make a much more economic system if you put these two buildings together, once again, if they're in close proximity. So that green line at the top, the combined demand, is a much more cost-effective demand than the two demands on their own. So here we're looking at a multifamily residential complex, a commercial demand profile. Putting them together, combining them, can provide a much more attractive, economically viable system. Next slide, please. CHP benefits for improved resiliency. I'll focus on the two Connecticut cases. Fairfield University, 4.6 megawatts of CHP. 98% of the town of Fairfield lost power, and Fairfield continued to run through Sandia. The university building served as area of refuge for off-campus students. Danbury Hospital, another instance of CHP providing continuous power during several emergency situations. UMass Medical Center, which ran through the October 2011 storm, operated in UMass Amherst as well. Amherst, the area around Amherst was out of power for 4 to 7 days, and the university was one of the only sites that continued to operate and serve the entire community. Next slide, please. This is, I thought, a particularly interesting case. South Oaks Hospital during Sandy was operated isolated from the grid for 15 days. When power was down, this provided 100% of the facility's electricity, thermal, and hot water demand during that entire 15-day period. They, in addition to meeting their own needs, they admitted evacuated patients from nearby healthcare facilities. They refrigerated medications and housed hospital staff who had lost power. Next slide. This kind of reiterates what I said previously. Well-designed CHP is highly efficient. This talks about efficiencies in several cases. Once again, trying to highlight the point that this is proven technology. We can show you any number of case studies. Next slide. Co-op City is another example. Co-op City is a little city in and of itself with over 55,000 residents, a 38 megawatt CHP system. The facility provided full power to Co-op City before, during, and after Superstorm Sandy. Next slide. Favorable characteristics. What should you be looking for? Well, there's a higher energy cost, concerns about power reliability. Over on the right side, though, also, I think what makes sense, do you have old boilers, old chillers? Is there a need, for a pretty imminent need for new upgrades, future facility expansion? These are the kinds of times when you want to look at CHP as an alternative. Next slide, please. I'm sorry to be rushing through this, but I just want to finish, and I only have 3 slides left, by talking about some of our tools. Our CHP Technical Assistance Partnership has several tools and resources. We can help in assessing economic viability, help you addressing interconnection issues, navigating legal and regulatory matters, understanding tariffs and standby charges. And as I mentioned earlier, we have some vetted models and tools, a first order microgrid or district energy screening tool, CHP technical assessment and qualification screening tools as well. Next slide, please. For those who may be interested, the first order district energy or CHP screening tool, it is not an investment grade audit, but it will provide you a lot of information. It includes regional load profiles, local, Connecticut-based energy prices, labor rates, financial rates, pipe costs, and so on, user inputs. You can look at the phasing of projects, your microgrid, how do you build it out over time, how do you finance it, life cycle costs, and it compares it against a couple of options, including the baseline. The baseline would be having individual boilers and purchase power from the grid. Again, this is not a detailed pro forma, but as that traffic light indicates, it helps you answer those questions. What do I do next? Is it a go or a no-go? It will help you with that type of an analysis. The screening, next slide, please. The screening tool parameters. We look at operating expenses, the energy costs, labor, maintenance, and consumables, capital expenses, and economic considerations. The outputs would include things like the net present value of the investment, the years to payback, the economic. Again, users can identify these and change them as you wish. What's the appropriate discount rate, escalation rates for electricity, natural gas, loan terms, and so on. Final slide, please. Or I guess it's not quite final slide. The next steps, if you're interested, please contact the Northeast CHP Technical Assistance Partnership and PACE. Next slide. This is our national network of 7 centers. We're up there covering the Northeast states, the Northeast CHP TAP. It has our website, northeastchptap.org. I'm co-director for economic and financial analysis and work with Dr. Becca Kosanovic, Professor of Mechanical Engineering. And final slide, please. And once again, there's our contact information should you wish to contact the DOE CHP Center or PACE, information for both myself and Professor Kosanovic. Thank you very much.
Okay, and thank you, Tom, and thank you to all our presenters. If we could, I think we have a slide showing all the presenters' names and contact information. Samantha, if you could put that slide up. I think it's at the end of my deck. There you go. So we're going to go right into questions. You could still submit questions at this point. Again, please indicate if you are a potential applicant to the program. And so the first question from a potential developer and applicant, is there a pro forma available that validates the economic viability of these technologies, especially since generation and storage are excluded from funding in the program? And I think what he means by that is that the grant money from Connecticut DEEP cannot be used to pay for generation and storage equipment, but for things like interconnection. Is the DSU $50,000 model that was funded by CEFIA in the first round available to participants? That's probably a question for Veronica, I would think. Veronica, you on?
Thank you, Todd. First of all, in the RFP, there is a pro forma criteria that are in there. Every installation, of course, is going to be different, but it lists, things to consider, and you do need to put together a pro forma in the RFP. And I'm not sure what they meant by the assistance from CEFIA. CEFIA is available to assist applicants in the second round of this program, connect them with financing for their generation. You just need to reach out to Genevieve Sherman at CEFIA, and she can, hopefully point you to partners for that. But other than that, I don't know what other specific assistance they're speaking to.
Okay, thank you. Second question from the same program participant, actually. Will microgrid customers receive a bill from the microgrid owner or the utility? And will a rate case be required? And are social costs waived or included for microgrid customers? I don't know if anybody can speak to that.
Todd, it's Veronica again. I ask that questioner please send the question into the DEEP site at deep.energybureau@ct.gov. We're trying, with a limited time, to answer topic-specific questions today, and DEEP will put out FAQs for general program questions in the very near future. So please send in your questions to DEEP.
Okay, great. Here's a question on energy storage. Please address the time frames of storage: seconds, hours, weeks.
Okay, I'll take that. Energy storage could go from seconds to hours. Weeks, you couldn't afford to do weeks. So you would probably go, right now, the power applications are seconds, up to the energy applications 4 hours. I think that's a reasonable amount of time. After that, it gets kind of costly.
Now I'm gonna pursue that a little bit, because when you say 4 hours, you're talking about 4 hours without 4 hours with just the storage device. But in this case, you have generation that would be recharging your storage device.
Yes, what I mean by that is 4 hours before you need to recharge. So if you have renewables or something that can charge,
very good. So
you can continue on forward.
Right. Okay. So in a microgrids situation, we're not talking about isolated technologies. We're talking about connected technologies and loads. So you would think about a microgrid situation where you would have perhaps storage, renewable generation, and either CHP or a fuel cell as a dispatchable device. And under that scenario, can you speak to the role of storage in terms of duration?
So, well, it could be immediate ride-through to get everything else up and running. It could be the ramp rate control on your renewables. So those are all short-term. It could be utilized for longer term, like if you have renewables. You would be able to, say, charge during the day and then discharge at night. So depending on how much capacity you have in your batteries, maybe and how much load you have, you might go all night until the next day, and then the PV would come back on and charge your system. I'm not quite sure how it would fit with CHP or with fuel cells. I'd have to look at that a little bit closer.
Okay, great. There's a couple of questions about fuel cells. One is simply, what exactly are fuel cells? And the second one is that Paul indicated the life cycle costs for fuel cells was competitive. What were the assumptions used for the price for natural gas and the escalation factor?
Okay, I'll jump in there. And again, I'm a lawyer, not an engineer. But a fuel cell is different than a recip engine and other fossil fuel fire type generation facilities, because it's actually done through a chemical reaction, my understanding. So there's no moving parts. It actually converts. They go on natural gas, and it gets converted to hydrogen within the system, my understanding, and then it's used to, make the energy. And so there's really there's very, very low emissions, very, very low emissions. But again, not being an engineer, that's sort of the extent of how I understand it. All I know is it's a chemical reaction generating the energy. And what was the second question?
Right. So the second question was, what were the assumptions used in whatever calculations were done to come to the conclusion that it was cost competitive? In other words, when you say fuel cells are competitive, you're making certain assumptions about the price of natural gas and how that may increase over time. And so what were those assumptions?
Yeah, I took those. I took data directly from the fuels, like for example, Claridge Power data that they provided, and to come to that conclusion. But again, they took into consideration the actual cost to operate the system. It is actually a little higher capital cost to buy the system, but the operating cost once the system is operating is much lower because there's very low maintenance. So I guess maintenance and the gas is more of a pass-through. It would be the same for other other types of technologies. But in order to really nail down that question, my advice would be to contact the manufacturers directly, and they can really lay out their analysis on why they believe they're competitive.
Okay. A couple of questions about CHP and CHP and storage. First of all, when CHP is combined with load management programs in a microgrid, is there still a need for storage? And I guess this is apart from any other uses of storage, such as regulating variable output from PV or wind. But strictly speaking, in terms of the management of the microgrid. So the question is, when CHP is combined with load management programs in a microgrid, is there a need for storage?
I can take that. There could well be, and there could be some good, it depends, there could be some good economics if I'm understanding the question correctly. And let me point to a case study, and this is not battery storage, but it's thermal storage. Princeton runs a large CHP system along with a thermal energy storage system and uses that strategically in demand response markets, but also strategically as a cost savings device. So buying very low cost power, charging up the thermal energy storage, using very low cost power at night, discharging it, and displacing very high cost power during the daytime. So that's one case in point that comes to my mind. And also you might be able to use it once again to even with the load shedding protocols that one would need to balance supply and demand within a microgrid, you might also use this strategically within RTO, or I should say in the case of the New England ISO programs, it might improve your ability to participate in ancillary service markets and other markets where there might be some additional revenue streams that could make your microgrid more economically viable. So those are two points that come to my mind, and one of them, actually both of them are being proved out at Princeton. Princeton is participating in ancillary services markets in PJM and does use their thermal energy storage system strategically as a cost-saving measure and as a way to operate in demand response markets.
Okay, so cost savings on the customer side of the meter and
revenue generation. Potentially
right.
Revenue generation from a new market like an ancillary services market.
Right, and we are seeing, just to explain a little bit further what you just said, there were a number of recent FERC orders that stimulated the creation or the changing of markets for ancillary service provision in ISOs and RTOs, and those orders have been adopted in various locations over time, and some of the areas are more compliant than others. PJM happens to be, I believe, the first to become compliant, and so it's an excellent market for providing those ancillary services. I don't know, Dan, did you want to jump in on this one at all before I go to the next question?
No, I don't have anything to add.
Okay. Then another CHP question, are controls available to manage old CHP sites with smart grid or microgrid operations? So I guess this is referring to a situation where you would have existing CHP, but can you retrofit it with some control technology in order to make it work in a microgrid setting?
Before answering definitively yes, I guess I would need to know more specifics about the situation, but I think I can give a general yes to that. You can take existing sites and reconfigure them to operate in that manner. Not knowing precisely, what one is thinking about doing, and hearing just 2 days ago from my friends at NYSERDA's R&D group that there are some challenges, and depending on how you want to manage multiple generation units, there may not be off-the-shelf controllers for doing that, certain functionality. I don't want to say yes to in all instances, but I think I can give a qualified yes that, if one has an existing CHP, there are certainly investments that could be made that would make it reconfigurable for a microgrid application.
Okay, thank you. A couple of questions about the technologies that use natural gas. This would include potentially CHP and fuel cells. And Veronica, you may want to jump in on this as well. Is it assumed that the natural gas infrastructure will remain functioning in a natural disaster? And how is that evaluated in terms of vulnerability, or I guess as a strength for a microgrid? And then also, what other fuels are sometimes used for CHP systems, and what are the pros and cons to consider in terms of fuels?
Okay, so I'll start with that then, Todd. So first of all, our program assumes that if you are using a natural gas-fired generator, that you have firm gas supply. So assumes that the natural gas system would still be operational, but you need to have a firm gas supply. And if you're using some other type of fuel source, you need to have 2 weeks of on-site storage, and an opportunity to secure an additional 2 weeks. So we do require a firm gas supply if you're using natural gas.
This is Tom. That's a really good question, and it's analysis that we would love to do. I can't give a definitive answer, but I can say that it's our supposition that the gas infrastructure system is more resilient, and that oftentimes when the electric system is down, the gas system is not. I can't give you the some specifics on the empirical correlation between the two. It's numbers we should have, but it's a research that we haven't undertaken yet. And in addition, you may be able to, and I believe this has occurred in round 1, where some sites propose utilizing microturbines that could be supplied by gas or run on propane. So you may have dual fuel capability and be able to use both the gas infrastructure or another fuel if you weren't being served by the gas infrastructure.
Okay, thank you. I can say that at least with regard to northeastern storms, we have seen numerous instances of outages due to things like lines being down, and that doesn't generally befall natural gas pipes. And the other thing that I wanted to throw in there to that question was there certainly are CHP systems that are biomass fueled. And I don't know, Veronica, do you have any comments on that in terms of the program requirements or restrictions?
There are no program requirements or restrictions I know of as far as that goes, except the diesel generation maximum and firm gas supply. If you're going to use that, access to fuel sources. So however you configure the generation to best suit your needs is acceptable under the program as long as those requirements are met.
Okay. Dan, this is a question for you. Somebody wanted to get more of a description or a definition of flow batteries. Can you speak to what a flow battery is?
So, well, if you take like a zinc bromide, basically it's a plating process where you have a tank of zinc bromide, and then you plate zinc. So when you're charging the system, basically you plate zinc, and then when you're discharging, you're unplating, deplating the zinc, and you're causing an electron flow. So it's like a plating process actually in the case of zinc bromide. In the case of, like, say, the iron chrome, basically you're flowing and you have you're flowing an electrolyte and you have an ion exchange going on, and so you're just flowing from one tank to another tank, and by you have these two dissimilar electrolytes, and you create an ion exchange through a membrane, and then that causes electron flow. So if you went to, if you went to the Electricity Storage Association, which I believe now has been changed to Energy Storage Association website, they used to have some slides on there to give the details, or you can go into the various companies, Enervolt being one for the iron chrome, ZBB being one for the zinc bromide, and then UET they have a vanadium process. You can get more information. I don't want to go too far into depth because I would be probably getting in over my head in exactly how the chemistries work.
Okay, thank you. If you just want to remind folks, if you're not actively speaking, please mute yourself. We're getting somebody's breathing into their microphone. If it's okay with everybody, I'm going to stretch this just a few minutes to take a couple more questions, and then we'll wrap up. Questioner wants to know what the range in kilowatts is for fuel cells, and actually this is probably a good question to throw out for all these technologies. What's the range? What are we talking about here in terms of what you could really expect to purchase and install, in the next year? What's the size range in kilowatts for these technologies? And let's start with fuel cells, and we'll go to CHP and storage.
Yeah, this is Paul. I can jump in on that. I know it depends on the manufacturer. For example, ChlorEdge Power, they have a 400 kW machine, I believe, and they have many other. I think they have a 400 kW machine, and they also have like a 10 kW machines also, and so it's pretty standard. That's what they provide. Fuel Cell Energy is another major fuel cell manufacturer. I believe their machines are bigger. I think they have it's in the megawatts, the low 1.4, or I'm not exactly sure exactly big, but it's under 2 megawatts, I believe. But they're in the 1 megawatt size. But I think a thing to remember too, for a lot of these machines, that they can be modulated so that you can have more than one to kind of increase the capacity. But again, there's limits on how small you can go. Like 400 kW is sort of the standard for one company. That's their machine. So that's it. I think that's it for fuel cells.
CHP. Well, that can go from the very small to the very large. You have micro CHP units based on reciprocating engines down to as little as under 2 kW, household 2 kW, based on Honda engines and the Marathon engine. So you're looking at 2 to 5 kW micro CHP. Probably not what you'd be utilizing in this program. But then the reciprocating engines on the larger scale, from small, nursing home size, 50, 60 kW, very small, or a small commercial establishment, up to half megawatt, up to several megawatts. And again, as Paul said, you can easily modularize these. So you could do something with 200 kW, or you could do several 3 by 400 kW, and so on. Gas combustion turbines typically become more economic in the larger size ranges, above 3 to 5 megawatts. When you're getting up 5, 10 megawatts, you might want to be using or looking at gas combustion turbines, also depending on what the use for the heat is going to be. As I mentioned before, you get a higher quality of heat, so that comes into your analysis as well. Microturbines, once again, from very small scale, but you can also gang them together or modularize them to multi-megawatt scale. So with the CHP, you can go up to very large units. You can be as small as the micro CHP serving a household, up to one of the slides I put up was Co-op City, almost 40 megawatts, Cornell University, over 30 megawatts, University of Texas Austin, over 100 megawatts, University of Texas Austin system, and also, by the way, running at 90% total system efficiency.
So that leaves energy storage. So that's a very good question for energy storage. It helps me explain a little bit more detail. So there are systems from 5 kilowatt range that people are putting in their homes, 30 kilowatt that they're using for community situations, 50 kilowatt, all the way up to 10, 20 megawatt systems. Once again, modularity comes into play, where you just take a system and you just keep adding those little shipping containers, if you will, to build it to the size that you need. One comment on the flow battery, which is nice, is the energy component. So the flow battery is separated into a power, which is your cell, and the energy, which is your tanks of electrolyte. And so one nice feature about the flow battery is if you want a longer energy capacity, all you need is to put in bigger tanks and more electrolyte. And then those can go for, I don't know, the sky's the limit on how much electrolyte you would have to flow through the cell stacks, providing you energy for longer and longer durations of time. So once again, it depends on your situation. You can go anywhere from 5 kilowatts to megawatts.
Okay, thank you very much. Sadly, I think that's the last question we have time for, since we are at this point 10 minutes over the time when we were supposed to end this webinar. If we could, Samantha, put up the slide that shows our website link, please, so that folks know where to go if they want to review the webinar. It will be posted there, I'm assuming, later today. There you go, webinar archive, that's where they're all kept, and there's also information for getting to the ESTAP website. And Veronica, any final words on this from Connecticut DEEP?
Just thank you to everyone who attended. I hope you found this helpful as you're preparing your proposals for our round 2 solicitation. We will answer questions in the FAQ, so if you've typed them in here, we will get to them in the FAQs. We didn't get to them today. And any additional questions, send directly into the Deep.Energy Bureau at cc.gov. Thank you.
Okay. And thanks to all of our presenters. A very good webinar. Samantha?
Thanks very much, everybody.